And in this case, essentially healthcare providers, they may share patient medical information with a specialist that may not be at the same location, right? And the second type, what we call real-time telemedicine. And this is kind of a simple scenario where patients and providers may use some video conferencing software like, Zoom, for example, what we are using now, or, Skype, to talk to each other and to allow patients to maybe understand their condition better, or to inquire about their health condition from a specialist. And then we also have the third type of telemedicine, remote patient monitoring. And, this is essentially where healthcare professionals are able to track a patient's vital signs, like, blood pressure or heartbeat rate and so on and so forth. So track this and also activities from a distance, right? So for this to happen, obviously, we need to use devices like sensors and things like, for example, even an Apple Watch or any device that can actually collect and measure or capture vital signs. And then after this data collection, obviously, there is a need to kind of transmit and send the data to for interpretation by specialists. Obviously, we don't assume patients to be able to interpret their own vital signs properly. So, this can happen. So this interpretation process can happen at locations like a home health agency, or an RDTF, or a doctor's office, or a hospital. So in traditional RPM, so the interpretation happens, so essentially is conducted by some healthcare professional, for example, a nurse. And the purpose essentially is to look at the data and to try to detect whether there is anything to worry about, whether there is an undesirable patient condition that's either happening now, or that happened recently, or so. So this is good, but so we would like to improve on this. We would like to have a system that provides more than what a traditional RPM system actually provides. And in particular, we would like to minimize the human intervention. Obviously, humans, they might make mistakes, and in general, it takes humans a lot more time to work on certain tasks than machines. And we also would like to provide healthcare professionals the ability to actually do more than detect undesirable patient conditions, but also to predict undesirable patient conditions. We obviously would like to avoid patients to go through unwanted healthcare episodes. So for this, we thought about combining two powerful things. So machine learning, and with all the power of the predictive power of machine learning techniques, and traditional RPM, and with obviously the ability to remotely actually have access to vital signs from patients and so on and so forth. And the result was something we called IRPM, Intelligent Remote Patient Monitoring. The word intelligent obviously comes from the use of machine learning techniques. So in this new model, the IRPM, we still obviously need to collect data from patients, obviously remotely. And we now want to actually predict health situations or health status. And when we detect certain unwanted conditions, generate some alerts that might be sent to directly to patients if necessary. And what we mean by vital signs here, things like body temperature, heart rate, respiration rate, and so on and so forth. We also, in our system, we use actually, in addition to the 7 vital signs that you see, we also used 4 demographic attributes. So the 11 attributes that you see here will be the input to our machine learning techniques that we are going to describe shortly. So before we talk about the details of our machine learning algorithms, let me just give you a quick overview of the system that we developed. So the system obviously is a cloud-based system. So all the components are deployed on the cloud, and the system is easily accessible by essentially all the stakeholders. So it can be accessed by professionals working at hospitals, by the patients themselves, by maybe insurance companies, by management organizations, and maybe also by government agencies. Obviously, the system will not provide the same interface to all of these people, but the system is still able to actually serve all of these different categories of stakeholders. So the system obviously uses a database that has a large number of readings. So essentially health readings related to vital signs from a large number of patients. And we'll describe our database in a minute. And in terms of software components, the system as of now has 3 major components or modules, and I'm going to describe each one in a minute. So the first one is the Intelligent ICU Patient Monitoring module. I think my mic is giving me a hard time. So the first one is the IICU-PM. And what this module provides a number of predictive mechanisms that ICU specialists can use to, for example, predict things like patient mortality. So whether the patient is likely to be discharged or is likely to die while at the ICU. Predict things like the length of stay at the ICU, whether readmission to the ICU for this specific patient, whether the patient can be put in an abnormal class of, in a class of abnormal patients, or whether the patient can be put in a normal, in a class of normal patients. Also predictions related to the values of the vital signs in the next day. And these can be very useful for ICU specialists. The second module of our system can be used by patients who may not actually be necessarily in the hospital. So this is why we called this module an out-of-hospital module. So users can use it to, for example, predict their heart rate abnormality, or for example, their SpO2 level, obviously based on data that's collected by themselves. So in this case, the input can be, for example, the heart rate levels, for example, in the last hour or in the last day, and the SpO2 levels in the last hour or last 10 hours or, last 24 hours. And the last module, the reporting module, can be used in general to provide summary information. For example, how many patients do we expect to receive in this specific ICU unit, maybe in the next 12 hours, in the next 24 hours? How many patients are we likely to discharge from the ICU unit in the next hour, in the next 10 hours, in the next day or so? And obviously you can see the benefit actually of using a module like this in terms of management of supplies and beds. So the next thing I wanted to talk about is to give you an idea about our database and essentially the data that we used both train and test our, the accuracy of our machine learning techniques. So we used essentially three major data sets. The first one is called the MIMIC3 data set, so the Medical Information Mart for Intensive Care. And this data set was developed by the MIT lab for computational physiology. And it spans a period of more than 10 years of ICU stays. It has a total of about 60,000 hospital admissions for adult patients. And in terms of data representation, so it has 26 tables that can be read as CSV files. And the total number of rows in those 26 tables are about 500 million rows. So that's the entire content of the database. The total size is about 50 gigabytes. And MIT currently actually requires users to actually go through training before they give them access to this large database. And obviously, we had to actually go through this training before they gave us access to the database. We also used data coming from Apple Watches, regarding things like the heartbeat rates, and so on and so forth. And we also used this device, which is called the SpO2 sleep ring, that gives you information like, the oxygen saturation levels in your body, and so on and so forth, just by putting this ring in your finger, and you can actually get readings for a period of time, and then you can actually transfer these readings using a USB cable. I'm going to pass it over to my colleague, Dr. Al-Gahtani, now for the rest of this presentation. Thank you.
In Intelligent ICU patient monitoring, we extract all the inputs from the MIMIC. We extract the vital signs, measurements, body temperature, heart rate, respiration rate, systolic blood pressure, diastolic blood pressure, and SpO2. Also, we include the glucose level. Some are considered a vital sign, other not. Demographic attribute, age, gender, weight, and height. Also, we extract from the MIMIC the real outcome of interest, the status of the patient if he discharged or death, the exact length of stay, if the patient readmitted to ICU in a single hospital patient or not. Also, if he is considered to be normal or abnormal. Also, the vital sign measurement on a daily basis, because we are going to build this model for 1 week. So we extract all of this information from the MIMIC. This is the step. First, we extract only the first day of the vital sign for each patient. And because based on the first day of the vital sign, we are going to predict the 5 models. We are going to predict if the patient will die or not. We predict how long the patient will stay, only based on the first vital sign, based on the vital sign of the during the first day admission. For that we discard all patients who stay in ICU less than 1 day. So in MIMIC we have 61,000 ICU stay. We extract all the vital signs. Here is about 60 million rows. Also the height and weight. We did some merging between the tables, and the output is that it's ready for a model. There was some missing data. We fill it with the mean of the population. I'm saying about 1%. Missing data is around 1%. So it's not that slow. Also, we eliminate unexpected measurement, minus or extremely extreme. Also, we did some feature scaling because I found that vital sign, they are not in the same scale. The range vary. For example, the normal heart rate for adults, based on my reference, is between 60 to 100 pulse per minute, but in respiration rate, the normal respiration rate for adult, based on my reference, is between 14 to 23 respiration per minute. So we need to have a scale because some machine learning algorithm very sensitive when the distance between the points matter. It is standardization and normalization. Now we will go to the data analysis. As I mentioned before, we are extracting the vital sign for the first day of staying. So what's happened? Some scholars, they just take the mean of this observation. So the first day, for example, the heart rate, it's taken every 30 minutes. So I'm speaking about 48 observation. And when you when you calculate the BDF, the probability density function, they take only the mean and use it as an input. This one. Second, sometimes they neglect the observation in the first or in the fourth quantiles because they consider it outlier. In our case, we will consider the baseline. We will consider the mean and use it for a baseline. Also, we'll not stop in this point. We'll do further process for the patient data to extract more information about the patient conditions and create new features that can be used later on as input to our model. So we are going to emphasize the quantiles. We found that the observation in the first and the fourth quantiles are very critical because most of patient deteriorating condition always come at high or level or low level of measurement. So what's happened? We isolate all observation in the first and the fourth quantiles, and we come with the new samples. We call it modified sample. In the modified sample, we calculate again the standard deviation. We calculate again the mean. Also, we count how many observation, and we'll use all of these three as an input to our model. This is the steps. This is the vital sign for the entire database from MIMIC, ordered by ICU state. In each ICU state, we'll see the vital sign list for the single patient, and it's ordered by vital ID. One is the heart rate, systolic blood pressure, until the glucose level. In each vital sign, we calculate the BDF. We calculate also the percentage point function, it's the inverse of CDF, just to isolate the observation in the first and the fourth quantiles. After that, we come with the new sample. In the new sample, we'll calculate the mean, we'll calculate the standard deviation, and we calculate how many, we count how many observations do you have in the first and the fourth quantiles. So for each vital sign, now we will have 4 inputs, 4 features, and since we have 7 vital signs, the total we will have 28 inputs for statistical approximation. I found that most of the researchers in the same field using these evaluation metrics. They use accuracy, they use ROC curve. It's a feasible method to plot the performance of the positive classes in the classification problem. And they use area under ROC, it's a scoring that has the ability to distinguish between the model classes, between the positive or negative. Also, we use RMSE and MAE for regression problem. We divide our population into 2 data sets, one for training, take 75, and one for test, only 25% of the entire population. Now we'll go to the predictive models and clinical applications. We create 5 predictive models to support patient in ICU without any information about the medical condition or diagnostic. Even though it's included in the MIC, but we didn't touch it because we only focus on using the vital sign and demographic attributes. We study and evaluate both approach, the statistical and the baseline. Also, we're going to show in this presentation only the highest model accuracy and area under row score after applying different machine learning algorithm. For the out-of-hospital module, we use a multi-layer perceptron. Now, the mortality model, the outcome of interest is the mortality is the in-hospital mortality, and we found that only around 12% belong to non-survival class. So we have now balanced classification problem, but imbalanced classification problems. In the interval stay, I found that the half of the population spent 2.64 days. So based on these days, we will create a binary and balanced classification problem. The first class to predict if the patient to stay 2.64 or the patient will stay more than 2.64 days. We create another version of this model using the regression problem to predict exactly how long the patient will stay in ICU. In abnormality, the goal of the abnormality model is to predict if the patient will show undesirable health condition. In our case, we have 3 death, long ICU stay. We decide to go with 7 days or readmission. We found that the majority is the abnormal patient group, so we remove some sample randomly to have a balanced classification problem. And the new total ICU stay is around 39,000. This is the result. You can see the first column, the model, and here the accuracy using the baseline and the accuracy using the statistical approach. And here's the improvement. You can see that the improvement in the mortality was very low because it's imbalanced classification, and the improvement in the interval stay is around 3%, and the improvement of abnormality is around 3.64. So if you see the last column, you can see the improvement of using the statistical approach. That support our idea that most critical observation, the observation in the first and the fourth quantiles, will make our model rich with data and will power our model, and without using any external features. You will use the same source of the data, patient data. And this is the result using the ROC curve. You can see here the relation between the false positive and the true positive rate. And you can see the performance of each algorithm, machine learning algorithm. We use the linear regression, linear discriminant analysis, and random forest, key neighbor node, and support vector machine algorithms. And here from the figure, you can see that the RF is the best. And here the score using score using the edge and the ROC. This is the second version of the interval stay using the regression. We found that support vector regression get the lowest error, and using our statistical approach. In the readmission, the outcome of interest is detect if the patient will readmit or not to ICU during the current hospitalization. We found that only around 5% from the population is belong to readmitted to ICU. So we have severe imbalance classification problem. So we have only 3,000 only belong to one classes. And the majority class is not readmitted to ICU. We have 41,000. So we have problem here. So we come with 3 solutions. The first one is just binary and imbalance classification. We don't do nothing. Second, and the sampling method, and that's by remove sample from the majority group until we achieve the same number of sample in the minority group. But what's happening in this? We remove it randomly, and maybe because we are removing sample randomly may lack diversity. and we will lose adequate rich information. We come with a solution clustering resampling approach. Choose some from different patterns. That means we are going to use a clustering algorithm. We used k-mean. And our hope is to maintain the variety of the population and make our dataset rich. Here's the workflow. In the population, we have 44,626 samples. In readmitted, only have 3,029. We'll do nothing in readmission. We'll pass it until the final step. But for group no readmit ICU, we are going to cluster the population into 5 clusters, and each cluster will select randomly 6.6 or 6 sample, and after that we'll merge all the subsample. We will have a sample with the same number of sample in admitted to ICU group. So the final model dataset is sample with the dataset. It's a balance. And the total sample is 6,058. This is the result. In the left, you can see the result using accuracy matrix. In the right, you can see the result using area under ROC matrix. In x-axis, we have the name of the solution, imbalance, and the sampling, clustering, sampling, and the same for the area under ROC. Also, I show the results using the different method, baseline, and the statistic approach. What you can see, using the imbalance, you get to the highest accuracy. You get around 93%. However, when you use the area under ROC score, you get a very low score. It's around the half, and that means our solution using the imbalance, the model cannot distinguish very well between the classes. I mean the positive and negative classes. Negative classes here, patient not readmitted, and positive is patient will readmit to ICU. When you use the undersampling solution, the accuracy dropped to 55, huge, but we have balanced classification problem. But in the area under ROC, it's better. So answering about 3% improvement. But when you use the clustering readmission, the accuracy is better than undersampling. We speak about 68%. And the area under ROC score, we achieve a reasonable score, speak about 0.73, and 30% improvement when you compare it to imbalanced classification. This one thing. Second thing, you can see that in all cases, the statistical approach performs better than the baseline. Here's the comparison of the result using the ROC curve. Here's an imbalance. All the performance is very close to half. That's bad. When you use the undersampling, it gets a little bit better, but when you go with the clustering readmission, it's better and better. In the next day vital sign measurement detection, we extract the vital sign for the 1 week. With the 3 approaches. The first one is day-by-day approach. That means consider only the last day. So based on the first day of vital sign, we'll predict the vital sign for the day 2. And based the vital sign of the day 2, we'll predict the vital sign for the 3rd day. This is the day-by-day approach. Just we'll consider the last day. Second approach is average measured, include all previous day. So to predict the vital sign for the 3rd day, we'll include the mean of the vital sign in the first and the second. The error adjustment approach, same like day by day, but we'll consider only the last day, but also we'll take the deviation error from the last day. Because what's happened? To predict the first day, second day, we'll take the first day. To predict the vital sign for the 3rd day, we will consider the vital sign in the 2nd day and the deviation error from predicting the vital sign in the 2nd day. Because what happened by end of the 2nd day, we'll get the real vital sign measurement And this is valid information, and you can compare it with the result, with our results, with our detected results, and you can see how the error is it small or big, and we can consider it, use it for the next iteration. This is a regression problem. We use the RMSE for that. This is the result, the error results for the 7 phytosine. For example, here in the heart rate, you can see in the x-axis the day, the error in the second day, the error in the third day, and this is the unit of the phytosine. What we found that average error has the highest errors. Average measured has the highest error in each phytosine. Second, we can see that the error adjustment in general achieve the lowest error. And from the date ID and from the error adjustment, since we only consider the last day, we found that using the most recent phytosine measurement achieved the least model. Also, the outcome, the measure output value, I mean, the phytosine output value, limit more in recent measurement. It's not the same with the in case of average approach. So taking the old information doesn't help. Now in the three next tables, it's comparison between our work and other researchers in the same field using the same database. I'm not going to explain everything, but we can notice two things. First, they're almost using a high number of features. But in our case, we are only using 11 features. As, for example, here they use 148, and they get area in the rock, very good area in the rock score. But in our case, we get 0.78. We achieve better than this scala because the input is very close, and you get better. In the length of steering model, they are not using balance. I haven't seen any research using balance because our target was 2.64 day, but they are using different target day. For example, here's 7. For example, here's 5, and they got good accuracy compared to our accuracy. However, I tried to make similar setup with this scala, didn't miss. By changing the target date to 5, here we will have imbalance classification problem. They use the neural network, so I get my own neural network. And but I'm using 7 phytosine, and for demographic attribute, they are using several inputs. I achieved very close to their result, the accuracy. So I get 78. For them, they get around 80. Actually, it's 79 something. The same also in the IC readmission. They use many features, and also this one they use a diagnostic code. In our case, I didn't use any medical condition information. I didn't include it, only just phytosine and demographic, and we get a good score, good accuracy score to compare it with other. And they are using imbalance classification. I haven't seen any research using Mimic to predict the phytosine and using balance classification. I haven't seen. Also for the abnormality, I haven't seen. This is based on yes. Now we'll present the two models in out of hospital modules. The one is for the first one to predict the heart rate normality. The total size of the input is 10,000, around 10,000 observation. This is time series problem. We learned the last 24 observation we keep it for the test, and we learned the model using a previous heart rate measurement based on the time step size. So we use different time step times to see the difference. We found that when you use less time step, for example, 240 compared to 1,400, 40, we get a lowest error. And that's gives us, as a result, we found that heart rate output value depend more in the recent measurement. The same here for the SpO2 and the heart rate abnormality. The size is bigger now. It's bigger at 20,000. And we use the last 9,000 position for a test. And we use different time step to learn our model. We found that when you use the less time step, we get less error. Now we go to the prototype. In our prototype, we have interfaces to allow hospital and out of hospital patient to access the system. We have the database. We build our own database. And we have machine learning. We learn the machine learning, make it ready to receive a request from the system. This is our website. We name it Cloud Internet Remote Patient Monitoring. I'm going to share the website.
Hello. I would like to ask if we could go a bit further to the conclusions because we are running out of time.
Register, and after that you can log in. It's just about the solution. So I create account before.
This is recorded. You could just maybe play it forward.
Hello, I don't have any voice anymore.
Can the organizers speed forward the video, please?
Okay. Now you can see the three modules: the report, Internet ICU patient monitoring, and out of hospital. In the report, you can see the previous entry. I'm going to create now, enter new cases with the patient ID, patient, let's see, second, write the age, female or male, and all the. Now, if you go to the report, this for the hospital one, so you can see all the results, all the record, and all for the patients. Also, you can see the what you can summarize. So number of patients admitted to ICU is 66. The total the detected length of stay for the entire 24. That means the length of stay in average is busy for 3.6. If the capacity of this ICU is 6 bed, it will be an average. It will be busy for the next 3.3 for the 3.5 days. And here they summarize how many patients were predicted to be survive, not survive, abnormal or normal, and how who do you think will readmit or not. Now I'll go to the out of hospital. I'm going to use the sleep O2. On this actually is my data. Okay. What's the idea here? The idea is I'm going to detect the mean and the max and the median of SpO and heart rate for the next hours. Okay. And based on our reference, the oxygen level, the normal oxygen level is between 94 to 98. So this gives us that for the next hour, the maximum heart rate, the maximum oxygen level is 96, and this is changed from the previous measurements. And this is the minimum 97, 95, and this is the mean. So we cannot see, here you can see the over or below threshold. All my measurements is good and good. For the heart rate, it's the same, but here the abnormal, the normal range is between 60 and 100. If it's not, if it's off or below the threshold, tell me yes. So I'm good. This is the max, mean, and I'll go back to my presentation slide. Yeah. Any question?
This was the last slide. I'm here if you have any questions. Thank you for your attention.
Okay, thank you very much. So thank you for this interesting talk. I think remote patient monitoring is indeed a very promising domain, and I believe it will be common in the near future. So questions of the audience to the presenters can be put in the public chat. So while waiting for questions, I also have a question. I am not so much familiar with the artificial intelligence part, but I have worked on different security related solutions in this area. And so I was wondering if you have considered privacy and security related requirements in your study. And if you did not integrate, do you have an idea on the additional impact it would have from user friendliness point of view, computation, scalability, and so on? And if you did, what exactly took you into account?
Thank you. So frankly, in terms of security, not really. Now, in terms of privacy, I don't know if I mentioned it in the beginning, but you know, MIT, when they give you access to the database, you don't actually see any specific information related to names or even the ages. Actually, they are kind of anonymized. Someone who is like, I don't know, 48, you may see that person like 50 or 46. So they, on purpose, they anonymize the database from all aspects. So you don't really like the location, for example, the age, even the demographics sometimes. So they did the privacy preserving aspect themselves. So we didn't work on that. And again, security now, we didn't touch on that.
Okay. I don't see a question for the moment in the chat. Yes, maybe another more philosophy-based question. How does remote patient monitoring impact on the accessibility of medicine for vulnerable groups and patients who are not having access to digital memories?
So what do you mean by digital memories? Like
digital technologies, I mean, what would be the impact for more vulnerable groups and patients that do not have such access to these technologies? Yeah,
so in fact, thank you. This is really the motivation behind this whole research. When Dr. Al-Qahtani started working on this a couple of years ago with me, the purpose, as I mentioned in the first slide, maybe you noticed his affiliation. He's affiliated with a very big hospital in Saudi Arabia, and the whole purpose of his research is to kind of build a system that can be used by people living in rural places in Saudi Arabia. So having access to like moderate telecommunications technologies, a phone or internet, maybe slow, and so on and so forth. So we took that into consideration, and as you saw from the prototype, all what's needed at this time maybe a few devices to collect those vital signs. And that device that we showed, we actually used it, and it costs like $150, I think, or a little less. So I mean, I guess even someone who is not really rich, I guess, can have access to those devices, and plus obviously an acceptable internet access. So the system is designed actually for that specific category of population.
Okay, that is really great. Yeah, for the moment, I don't receive any more questions in the chat, and we also reached the end of the session slot, in fact, till 4 o'clock. So
okay, it's 9 o'clock here.
Yeah, I think yeah, congratulations. Thank you very much for this interesting talk.
Yeah,
And
thank you.
yeah,
Okay, thank you.
good luck with the research further.
Thank you. Thank you. Bye.
Thank you all. Bye.
Bye.